I think to understand disease and to understand the human condition, we need to understand how things work. Here on the Bethesda campus of NHLBI, we are working in basic biology, looking at protein structures. We're doing cell biology, understanding how cells work, and then finally working on the human condition. That is clinical studies, population studies, and then applying that information both ways. Taking the clinical data to drive the basic sciences, taking the basic sciences where we get opportunities to impact what the clinicians are doing around the world. My name is Bob Balaban. I'm the scientific director for NHLBI and the laboratory chief of the Laboratory of Cardiac Energetics. If there's one hallmark of our intramural program, it's in the area of imaging. That is trying to visualize proteins, visualize what cells do, visualize what happens inside your body, and use that information to better understand disease, but then to come up with better therapies. One of the things I've been working on for a long time is trying to get a better understanding of how the body deals with water. We're 70% water. I've had a great opportunity for many years to be studying this phenomenon using magnetic resonance imaging, which is basically an imaging method of water. One of the frustrating things is that the resolution of the MRI is rather poor. We can't see inside cells. We can only see gross structures. So we developed and worked on optimizing a technique called coherent anti-Stokes resonance spectroscopy, which is called CARS. How this technique works is by measuring the actual vibration of the water molecule and using that vibration signal, we can actually image its presence inside the cell on a subcellular scale. We'd never been able to see water on the submicron scale, and the question we were addressing was, how does the artery work? That is, the heart pumps blood at high pressure throughout your body. Somehow it does that at high pressure without leaks in your arterial system. But we didn't really know how the vessel, the artery wall, prevented water from leaking out. So these studies using the CARS microscope permitted us to find that there is a very specific position in the arterial wall where the water is blocked or prevented from moving forward. What happens is the pressure and the water move right through the endothelial cell, and this barrier to water, which sits right on all the large macromolecules that then absorb that energy. So here's a case where imaging, you actually saw the process, and in retrospect, you went, wow, that makes sense. And so now we understand where that barrier is. We start looking at disease states. What happens when you have atherosclerosis? Does this barrier break down? How are drugs moving? If this is blocking water, one of the tiniest molecules in the body, what's happening when we're trying to administer a drug? Where is it getting blocked and where is it getting concentrated? So those are the types of questions that we're now addressing. There's a wonderful history of the Bethesda campus having a tremendous impact on health. Engineers, physicists, chemists, cell biologists, and clinicians all working together, bringing a lot of the state-of-the-art technology to the understanding of biology. I think that's one of the beauties of this program. We let the investigators try to find those areas where they could have a keen insight into biology, keen insight in diseases, and potentially keen insights into therapy and make our lives a little better.